Part 3. Scaled animation is the third in a series of 5 videos, which are intended to explain what the Willet Buoyancy Engine is and why it could be a useful addition to the power generation options that are currently available. In Part 2, System Schematic, the operating principles of the buoyancy engine were explained. This video shows a scaled example in which the system design is geared to wave rather than tidal power as indicated in Part 2. This is intended to show an example of the working application and to introduce the main system components. This is not meant as a detailed system design and certain components aren't shown. In simple terms, the 3 components which are seen bobbing on the surface of the ocean pull the storage vessel towards the floor each time the swell lifts them. As the swell ebbs, a ratchet pulley system with a 2-to-1 gearing ratio holds the storage vessel in place. The animation shows a simplified waveform, which has been shortened in length and time for the purpose of this presentation. The pontoon is made up of a series of plastic tubes, which are arranged in a donut shape, each with a 3.5 metre diameter and 100 metre diameter overall. These are stacked to give an air capacity, which is a little greater than 67,000 metres cubed. A pulley wheel is slung below the body of the pontoon. This pulley is 20 metres diameter and includes a hydraulic gearing system, which is served by a number of power packs, a compressed air reservoir and a piston drive unit. The hydraulic gearing systems are repeated on each drum and pulley set and are used together to maintain tension on each of the cables at all times and to power the clamp jaws. The jaws may be operated remotely to allow attachment and release from the anchors. This feature is used during assembly of buoyancy engine, as can be seen in Part 4, Construction Animation. Maintenance is also made easier since each component can be detached from its anchor and craned to the surface, where it may be swapped out for a replacement component and shipped back to land. The control system constantly monitors the movement of the pontoons and regulates each pulley and drum set according to the cycle requirement. When 2 pontoons are rising together, there is sufficient force to pull the storage vessel towards the ocean floor. This is done by fixing outer drums associated with the rising pontoons. When a pontoon descends, the spare cable is wound onto the other drum, whilst the storage vessel is held in place. The wave is made up of vertical and lateral elements of motion. The control system is designed to utilise both elements of the motion when it is beneficial to do so, and to provide work as necessary via the hydraulic gearing systems to prevent excessive pontoon drift. The system will include remote status indication and fail-safe modes of operation should a malfunction occur. The ocean to the northwest of the UK shows significant wave height of 4 to 5 metres, which would represent a viable location for this system. The animation shows an area of ocean floor measuring 800 by 800 metres and a depth of 2 kilometres. Oil rigs are typically designed to withstand the effects of 15-metre waves, despite this being a rare event. In the same way, value engineering will place limits on the wave height, in which the buoyancy engine can safely operate. Thanks to a great deal of research into wave and weather prediction, these services will provide adequate advance warning. When the operation constraint is likely to exceed, the system will enter into a hibernation mode. Here the pontoons will descend to a depth where the worst effects of the ocean are avoided. The storage vessel is seen to rise and one by one each pontoon is pulled towards the ocean floor. Owing to a gearing ratio, the storage vessel will descend 2 metres for each metre of pontoon descent. Once the operating conditions are within operational constraints, the pontoons are used in pairs to lower the storage vessel and normal operation is resumed. The body of the storage vessel is similar to the pontoon, but the walls are thicker to cope with the crush pressure at depth. This helps to serve an extra function in that the storage vessel must remain buoyant when full of water in order to return to the surface at the end of each generation phase. The pipework header includes a sluice valve, shown in red, for each spur. When the storage vessel has reached the desired depth, it is ready for the generation phase. The sluice valves may be opened remotely to suit demand requirements. This is very useful for power operators since they must match generation and demand at all times. Availability of other renewable power generations such as wind and solar power is often less predictable since they lack the stored energy element of the Willet buoyancy engine. When the sluice valves are opened, water rushes into the storage vessel. En route, the water passes through a turbine, which in turn drives the generator. Air within the storage vessel is allowed to compress and is used to recharge the compressed air receivers, which are mounted on each of the drum and pulley sets. This is done via a network of flexible pipework. This pipework isn't shown but connects each of the drum and pulley sets. Air is then relieved into the atmosphere to ensure maximum electricity generation. Excess pipework slack is taken on drums to take into account the travel of the storage vessel. This is a scaled-down version of the main cable drums. Above and below the storage vessel core is a mesh. This allows water to flow but prevents larger marine life being drawn through the turbine. At 2 kilometres, the buoyancy engine will generate around 300 megawatt for 1 hour at a flow of 18 metres cubed per second, or around 600 megawatt for half an hour at a flow of 36 metres cubed per second for each cycle. For this location, a cycle will typically comprise 1 to 2 hours for storage vessel descent, 1 hour for the generation phase, 1 hour for storage vessel ascent, and another hour for purge phase. This provides availability for around 5 cycles per day for one system, but the notional business case will be based on an array of 9 systems operating together. In practice, the size of the system would be based upon the demand profile. Taking into account government incentives such as feed-in tariff, renewable obligation certificates and energy export rates for the generated power, along with estimated downtime and operation consumption, the annual revenue for each buoyancy engine would be around £84 million. Over 20 years this gives us around £1.5 billion, and for 9 systems over 20 years the revenue would be in order of £15 billion. In Part 5, Business Case, a rough order cost of the system design, manufacture, construction and through-life costs will be made and used to establish a likely return on investment. Thank you for taking the time to view this presentation. I would welcome any inquiries or questions relating to the buoyancy engine, which is patent protected.